Picture this. You're sitting in a Cincinnati garage in 1985 watching a perfectly good engine get torn apart. The owner thought it was driver error. The dealership blamed bad gas, but the mechanic crouching over that engine block, covered in oil and frustration, knew the truth. This wasn't an accident. This was a decision. A decision made in a boardroom, calculated on a spreadsheet, and signed off by people who would never once turn a wrench in their lives. And the worst part? It was just one of thousands of decisions, exactly like it, buried in filing cabinets across Detroit, hidden behind legal language and warranty fine print, while millions of Americans drove vehicles with known, fixable, deliberately unfixed flaws. This is legacy motoring, and I spend way too much time thinking about the engineering decisions that Detroit made behind closed doors, the ones that saved them pennies and cost us fortunes. If you're someone who wants to understand the real story behind why your GM vehicle failed, how backyard mechanics found solutions that billion-dollar corporations refuse to implement, and what the automotive industry doesn't want you to figure out on your own, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing. We talk about corporate scandals all the time. Enron, Volkswagen's emissions cheating, the Ford Pinto fuel tank. But what General Motors did over 4 decades with its small block V8 engines, its automatic transmissions, its cooling systems, and its luxury power plants, this was different. It wasn't one scandal. It wasn't one product line. It was a systematic, documented, internally acknowledged philosophy of building things just well enough to avoid catastrophic lawsuits, and not 1 cent better. And while GM's accountants were running their spreadsheets, a network of mechanics across America were quietly, stubbornly, brilliantly solving every single problem for a fraction of the cost. This is that story. Let's go back to 1955. Ed Cole's team at Chevrolet introduced the small block V8 and genuinely changed the automotive world. It was lighter, more efficient, and cheaper to manufacture than anything Ford or Chrysler had. By 1967, over 100 million had rolled off assembly lines. It was a legitimate engineering triumph. But from the very beginning, there were problems. Not accidental problems. Not problems born from ignorance. Problems that were documented in internal reports, analyzed by engineers, and then filed away because fixing them cost money that the accountants decided wasn't worth spending. Take the oil galley plugs in the 350 cubic inch V8. These small steel plugs seal the passages that channel oil through the engine block. They're not glamorous components. They're not the kind of thing that makes a brochure, but they're absolutely critical. GM's own internal testing in 1969 showed clearly that these press-fit plugs had a tendency to dislodge under sustained high RPM operation. The fix was embarrassingly simple. Thread the holes and use screw-in plugs. The cost per engine, 37 cents. GM's response? Keep using the cheap press-fit plugs and let warranty claims absorb the damage. Now, you might be thinking, surely they just didn't know how serious the problem was. Here's what most people don't realize. Patent number 3 to Monnier 8279, filed by General Motors in 1968, described exactly this threaded galley plug system for high-performance engine applications. GM knew the solution. They patented it. They used it in Corvette ZL1 engines. They used it in Corvette ZL1 engines. They used it in Can-Am racing applications. But the millions of 350s going into pickup trucks, family Camaros, and station wagons driven by working people across America got the 37-cent press-fit version that GM's own engineers had flagged as inadequate. Enter Mike McZidden. In 1982, a customer rolled into his Cincinnati garage after losing an engine on Interstate 75. The vehicle had less than 40,000 miles on it. When Mike pulled that engine apart, he found a missing galley plug and oil starvation damage throughout the bottom end. The bearing surfaces looked like someone had worked them over with sandpaper. The crankshaft was scored beyond any reasonable repair. Total damage, a complete engine rebuild. But Mike didn't just fix the engine and move on. He started asking questions. Why did this plug blow out? Why was it press fit in the first place? And most critically, did anyone at GM know this could happen? 3 weeks of research at the Cincinnati Public Library, digging through technical service bulletins, patent filings, and engineering publications gave him his answer. GM absolutely knew. They had engineered the solution, patented it, and chosen not to use it. His fix was humbling in its simplicity. He drilled out the galley holes, tapped them to accept standard pipe threads, and installed 15-cent brass plugs with thread sealant. The whole modification took 20 minutes and cost less than $3. The engines he modified this way were still running 2 decades later. Word spread through the Cincinnati racing community first, then through Ohio, then westward across the country. By 1985, Mike was fielding calls from mechanics in California, Texas, and Florida. Everyone had seen the same failure. Everyone wanted the same fix. What started as one man's curiosity in one garage became an underground movement that would span the continent. Here's where it gets really interesting. The galley plugs were just the beginning. Once mechanics started looking with informed eyes, they found compromises everywhere they looked. Flat tappet camshafts that would wipe lobes catastrophically if he didn't use a specific oil additive, an additive that GM quietly removed from their recommended formulation in 1988 to save money on licensing fees without updating any of their owner documentation. Cylinder head bolts manufactured from grade 5 steel when grade 8 would have cost an additional 4 cents per bolt. Intake manifold gaskets made from a composite material that GM's own internal testing predicted would fail after 60,000 miles of heat cycling with an estimated 90% failure rate by 100,000 miles. The response to that projection? Keep building them until 2003. The 4L6TE automatic transmission tells perhaps the most infuriating version of the story. This electronically controlled 4-speed was GM's workhorse transmission from 1993 through 2013, going behind everything from S10 pickups to the Tahoe, one of the most common transmissions in American automotive history. And it had a fatal flaw that GM tracked internally from the very beginning. The sunshell gear, a critical component in the transmission's planetary gear train, was manufactured from powdered metal rather than forged steel. The reason was pure accounting. Powdered metal parts cost $3.40 less to produce. The consequence was a component that would crack and split under heavy load, causing complete transmission failure. GM's own durability testing showed a mean time to failure of 72,000 miles under normal driving conditions. Under towing conditions, the number dropped to 35,000 miles. This was not a surprise. This was a projection. They knew exactly how long these transmissions would last and chose to build them anyway. Danny Rodriguez in Houston became the sunshell expert entirely by accident. His shop specialized in fleet maintenance, and by 1999, he was seeing 4L6E failures on a weekly basis. Always the same symptom, always the same component, always the same story. A truck that had been used for exactly what trucks are advertised for, towing, hauling, working, and a transmission that simply couldn't handle the demands GM's own marketing promised it was built for. Danny started sourcing aftermarket sunshells manufactured from forged steel. They cost $38 compared to GM's $22 powdered metal units. The installation required complete transmission disassembly, which wasn't a quick job, but the modified transmissions were coming back for oil changes and tune-ups rather than rebuilds. He was seeing these transmissions run 200,000 miles without a single major issue. The math was obvious to anyone willing to do it honestly. $16 in upgraded parts prevented thousands of dollars in catastrophic failure. But Danny didn't stop there. He started buying failed 4L6DE units from junkyards for next to nothing, rebuilding them with upgraded sunshells and a collection of other improvements he developed over years of studying failure patterns and selling them to customers at half the price of a GM replacement unit. His upgraded builds included improved servo pistons, better valve body separator plates, and hardened input shafts. Total cost and upgraded components above stock spec, roughly $150. The result was a transmission that was, without any exaggeration, more capable and more durable than anything that had ever come out of a GM factory. By 2002, Danny was shipping rebuilt transmissions nationwide. He had a waiting list. Customers were driving from 3 states away to get a Rodriguez-built 4L6E because word had gotten out that his units simply didn't fail the way factory units did. And what was GM's official response to the mounting evidence of systematic sunshell failure? In 2003, they quietly updated the sunshell design, but only for certain applications. Trucks rated for heavy towing got the improved forged component. Everything else, every regular cab half-ton, every SUV, every family vehicle that might occasionally pull a boat or a camper, continued receiving the same powdered metal unit they'd been installing since 1993. Look, I want you to think about what that decision actually represents. GM had the data, They had the failure rates. They had the fix sitting right there, a $16 upgrade that would have solved the problem entirely. They chose to implement it selectively, protecting themselves against the most obvious warranty claims from commercial users while continuing to install inadequate components in the vehicles driven by ordinary families. That's not an oversight, that's a policy. The Northstar V8 represents what is probably the most egregious chapter in this entire story, and that's saying something given everything we've already covered. This engine debuted in the 1993 Cadillac Alante as GM's answer to the German luxury performance market. Dual overhead cams, 4 valves per cylinder, aluminum block and heads. On paper, it was genuinely impressive engineering. In practice, it had a fundamental structural flaw that GM's own engineers had identified before a single production engine was assembled. The cylinder head bolts threaded directly into the aluminum engine block. Under the extreme thermal cycling of normal engine operation, aluminum expands and contracts at a different rate than the steel bolts. Over time and mileage, the aluminum threads would gradually lose their grip. Head gasket failure would follow. Coolant would enter the combustion chamber. The engine would destroy itself from the inside. The solution was not exotic or expensive. Mercedes-Benz used it. BMW used it. Honda used it. Honda used it. Steel-threaded inserts, or alternatively, longer bolts that reached into the stronger lower portion of the block where the material could maintain adequate clamping force. The cost difference per engine was approximately $18. GM chose not to implement either solution. Jake Morrison operated a shop in Detroit, right in GM's backyard, which adds a particular irony to what follows. Starting in 2001, Jake began developing a repair procedure for Northstar head bolt failure that involved installing steel-threaded inserts using a specialized drilling jig he designed and fabricated himself. The repair required 8 hours of labor and cost customers approximately $1,500. A replacement engine from GM ran $8,000, and here was the darkest part of that comparison. The replacement engine had the exact same design flaw. It would fail exactly the same way on the exact same timeline. Jake's repair kit became something close to legendary in professional mechanic circles. He started selling the kit to other shops for $300. It included the custom drilling jig, specialized taps, 64 steel inserts, and a documented repair procedure with detailed photographs at every critical step. By 2005, he had sold over 1,000 kits to mechanics across the country. When you work through the arithmetic on GM's total Northstar production, approximately 1 million engines built between 1993 and 2010, and apply the failure rates that Jake was observing in his shop, you arrive at a number of affected vehicles somewhere around 300,000. 300,000 Cadillac owners who bought luxury vehicles and discovered that the luxury didn't extend to the engineering beneath the hood. Here's what most people don't realize about the Northstar situation. Internal GM documents that surfaced during a warranty dispute in 2004 revealed that GM had been actively tracking Northstar head bolt failures since 1994, just 1 year after the engine entered production. Their internal failure rate projections showed 18% by 60,000 miles and 34% by 100,000 miles. And there was a document from a 1995 engineering meeting that laid out the proposed response in language that is difficult to read without genuine anger. The instruction was to monitor warranty costs versus repair implementation costs on a quarterly basis. They had a spreadsheet, a literal spreadsheet calculating how much money they would save by allowing engines to fail compared to what it would cost to fix the design. Their internal break-even analysis showed that if fewer than 22% of engines failed within the warranty period, it was more profitable to pay for those repairs than to redesign the head bolt system. Their actual warranty failure rate came in at 19%. They beat their own cynical projection by 3 percentage points and called it a success. Let that sit for a moment. A company sold people luxury vehicles, knew those vehicles contained a fixable design flaw, calculated the exact percentage of customers they could afford to disappoint, and then managed to that number like it was a production target. The customers whose engines failed outside the warranty period, the ones facing $8,000 repair bills on vehicles they bought in good faith, they weren't a quality problem to be solved. They were a line item that had already been budgeted for. The Dex-Cool situation adds yet another dimension to this pattern, and it's particularly instructive because it shows how GM's cost-cutting decisions could cascade across multiple vehicle systems simultaneously. In 1995, GM switched from traditional green antifreeze to an extended life orange coolant they branded as Dex-Cool. The marketing positioned this as a technological advancement, a coolant so superior it would last 150,000 miles between changes. What the marketing did not mention was that GM's own internal testing had shown that Dex-Cool would form acidic compounds when exposed to air pockets within the cooling system. Here's the problem with that finding. Air pockets in a cooling system are not a rare or unusual condition. They occur in virtually every GM cooling system as a result of completely normal operation. Temperature changes cause expansion and contraction. Tiny amounts of air get trapped. Under normal circumstances with traditional coolant, this is a non-issue. With Dex-Cool and its documented tendency to become acidic in the presence of air, it became a systematic problem affecting millions of vehicles. The acidic coolant attacked intake manifold gaskets, it corroded heater cores. It clogged radiators with a thick brown sludge that mechanics across the country started calling GM mud, because once you'd seen it in enough vehicles, you knew immediately what you were looking at and what had caused it. Bob Tyndall in Milwaukee developed the Dex-Cool deletion procedure that became standard practice in shops dealing with high volumes of GM vehicles. His flush protocol used specific chemical sequences to neutralize the acidic compounds before introducing traditional coolant. Total customer cost, roughly $200. He also sourced intake manifold gaskets manufactured from a different material that could withstand Dex-Cool's corrosive properties. These gaskets cost $12 more than the stock components. GM was aware this material existed. They had evaluated it. They chose not to use it in production until 2006, 11 years after introducing a coolant that their own testing had flagged as problematic. GM eventually settled a class action lawsuit related to Dex-Cool for $150 million. Throughout the litigation and even after the settlement, they continued to publicly characterize Dex-Cool as a superior product and maintain that the problems customers were experiencing resulted from improper maintenance rather than flawed engineering decisions made in their own laboratories. The 5.3-liter Vortec engine carried GM into the new millennium with genuine promise. It was more refined than its predecessors, more powerful, more efficient, and it came equipped with a technology that GM marketed aggressively as proof of their forward-thinking engineering philosophy. Active fuel management, later rebranded as dynamic fuel management, would deactivate 4 of the engine's 8 cylinders under light load conditions to conserve fuel. The concept was sound. The execution was a disaster that GM saw coming and shipped anyway. The system relied on specialized lifters that could collapse on command, effectively disconnecting 4 cylinders from the valve train when full power wasn't needed. Under light highway cruising, you'd theoretically be running a 4-cylinder engine in terms of fuel consumption, while retaining the capacity to summon full 8-cylinder power when demanded. It was elegant in concept. The problem was the lifters themselves. They were complex, oil pressure-dependent mechanisms operating in an environment that punished complexity, and they failed. Consistently, predictably, and well within the service life that any reasonable customer would expect from a modern engine, the failure pattern was always the same. Between 50,000 and 80,000 miles, lifters would collapse and refuse to return to their active position. The result was a misfire on the affected cylinders, a check engine light, and a repair bill that started at $4,000 once you factored in the labor required to replace all 16 lifters and the camshaft that typically sustained collateral damage during the failure event. GM's own internal tracking showed the failure rate was not a fringe occurrence. This was a widespread, systematic problem affecting a significant percentage of the millions of vehicles equipped with the system. Steve Daniel in Dallas found a $20 solution, a small plug-in module that intercepted the signal telling the engine control unit to activate cylinder deactivation. No activation signal meant the lifters stayed in their normal operating position at all times. No abnormal wear. No collapse. No $4,000 repair. Fuel economy dropped by perhaps 1 mile per gallon under ideal conditions, which was less than the real-world difference most owners ever measured. Engines equipped with his module were routinely hitting 200,000 miles without lifter issues, while their unmodified counterparts were failing at a fraction of that mileage. Now, you might be thinking that GM would have some legitimate objection to this kind of modification, some technical reason why defeating the system created problems of its own. Their actual objection, delivered at an industry technical conference when the question was raised directly, was that defeating emissions control systems constituted a federal violation. Here's the thing. Active fuel management was not an emissions control system. It was a fuel economy feature. The emissions equipment on these vehicles, the catalytic converters, the oxygen sensors, the EGR systems, none of that was touched by the delete module. It was a misdirection, a legal-sounding non-answer designed to discourage a conversation GM didn't want to have publicly. Mechanics kept installing delete kits, customers kept requesting them, and GM kept selling replacement lifters and camshafts to the customers who didn't know the fix existed. By the time GM finally acknowledged the scope of the problem and began working toward a more durable lifter design, the delete kit community had grown into a substantial parallel industry with multiple competing products, installation guides, and a customer base that had completely lost faith in the factory system. The fix GM eventually developed for newer engine generations, a more robust lifter design with improved oil channels, was functionally similar to what aftermarket engineers had been recommending since the early days of the failure pattern. It just took GM considerably longer to arrive at a conclusion that independent mechanics had reached in the first few months of seeing failures roll through their shops. The Vortec cylinder head cracking issue deserves its own detailed examination because it illustrates something particularly frustrating about GM's approach to known engineering deficiencies. The Vortec 5.7-liter engine introduced in 1996 featured cylinder heads that genuinely represented an improvement in airflow and combustion efficiency over previous designs. They flowed better. They made more power. They were a legitimate step forward in terms of performance engineering. They also cracked. Specifically, they developed cracks between the valve seats and the spark plug holes, in exactly the location where thermal stress concentrates during normal engine operation. Tom Caraway in Tucson, Arizona, saw his first cracked Vortec head in 1998. The truck had 42,000 miles on it, barely broken in by any reasonable standard. By 2001, he was seeing 2 or 3 cracked heads every single month. His solution was methodical and effective. He would have the heads professionally welded by a specialist he worked with, then machine small stress relief grooves around the valve seats to interrupt the crack propagation path before it could develop. The entire process took 2 hours and cost the customer less than $200, parts and labor combined. A replacement head from GM cost $800 plus labor, and the replacement head, manufactured to the same specification as the one that had just failed, would develop the same cracks on the same timeline. Tom did something that distinguished him from most mechanics dealing with these issues. He started keeping records, detailed records, photographs of every cracked head, mileage at failure, VIN numbers, operating conditions as reported by the owners. By 2003, he had a database documenting over 400 individual head failures from his shop alone, a statistically significant sample that painted an unambiguous picture of systematic design inadequacy. He attempted to share this documentation with GM through their technical assistance hotline, the channel theoretically designed for exactly this kind of field feedback from professional technicians. GM's official response stated that they were not aware of any systematic issues with Vortec cylinder heads. Internal GM documents later produced during a class action lawsuit told a different story. GM's own quality tracking systems showed a 34% failure rate for Vortec heads. 34%? That means more than 1 in 3 of these heads would crack. And GM's written response to a mechanic presenting documented evidence of the problem was that they weren't aware of any systematic issues. The gap between what GM knew internally and what they were willing to acknowledge externally was not a matter of degrees. It was a complete inversion of reality, maintained deliberately and consistently in the face of mounting evidence. The metallurgical solution had been identified during the engine's development phase. GM's own materials engineers had recommended using an aluminum alloy with higher nickel content for the cylinder head castings. The higher nickel formulation was more resistant to the thermal cycling that caused crack initiation. The cost difference per head was $12. For a V8 engine with 2 heads, that was a $24 difference per engine. GM's production volume for this engine ran into the millions of units. The aggregate savings from using the inferior alloy were substantial. The aggregate cost to customers dealing with premature head failure was substantially larger, but that cost wasn't on GM's balance sheet. It was distributed across hundreds of thousands of individual repair bills paid by people who had no idea that the failure they were experiencing had been anticipated, analyzed, and accepted by the people who built their engine. This is where it gets really interesting. Because when you step back and look at all of these individual cases together, the galley plugs and the sunshells and the Northstar head bolts and the Dex-Cool and the AFM lifters and the Vortec heads, a pattern emerges that is more coherent and more troubling than any individual failure story. These weren't isolated engineering oversights occurring randomly across different product lines over different decades. They were expressions of a unified corporate philosophy that had been formalized into actual decision-making frameworks. The documents that emerged from GM's 2009 bankruptcy proceedings were illuminating in ways that went beyond any single product liability case. Among them was an internal analysis document titled "With the kind of bureaucratic neutrality that makes genuinely disturbing content easier to read without fully processing what you're looking at." The document laid out the mathematical framework GM used to evaluate whether engineering improvements were worth implementing. If the cost of improving a component exceeded the projected warranty savings by less than 40%, the improvement would not be approved. That 40% buffer represented the profit margin GM expected to capture through part sales for out-of-warranty failures on the unimproved component. Read that again slowly. They were not just calculating whether to fix problems based on warranty cost savings. They were factoring in the revenue they expected to generate selling replacement parts to customers whose vehicles failed after the warranty expired. The out-of-warranty failures were not a cost to be minimized. They were a revenue stream to be preserved. Fixing the problems too thoroughly would have reduced demand for replacement components, and that demand had been built into the financial model that justified not fixing them in the first place. This is a part of the story that tends to produce a particular kind of silence when you explain it to someone who hasn't encountered it before. Because it forces a recalibration of how you think about the relationship between a manufacturer and the people who buy their products, we tend to assume, without really examining the assumption, that manufacturers want their products to last. That durability and reliability are goals the company is genuinely working toward, even if they don't always achieve them. What the GM documents reveal is something more complicated and considerably more cynical. Durability was a variable to be optimized, not maximized. The optimal level of durability was the level that minimized warranty costs while maximizing parts revenue from post-warranty failures, and they had the math to prove exactly where that optimum sat for each component family. The mechanics who were solving these problems one at a time in garages across America were not operating with access to these internal documents. They didn't need them. They could see the pattern in the failures coming through their shops. They could see that the problems were too consistent, too predictable, and too easily fixed to be genuine engineering mysteries. They knew, even without the documentary evidence, that someone somewhere had made a decision. And they responded to that decision the way skilled craftspeople always respond to institutional failure. They fixed it themselves. Rick Santos in Phoenix created a website called GM Problems and Solutions in 2008. Within 2 years, it had accumulated over 50,000 registered members, professional mechanics and informed enthusiasts sharing failure documentation, repair procedures, part numbers for upgraded aftermarket components, and the kind of accumulated institutional knowledge that GM was actively working to suppress. The site became something genuinely unprecedented, a crowdsourced engineering database that was in many respects more comprehensive and more accurate than anything GM's own technical documentation contained, because it was built by people who were motivated by solving problems rather than managing liability exposure. GM's legal department sent Santos 3 separate cease and desist letters. He ignored all 3. The site remains active today, still accumulating knowledge, still helping mechanics and owners understand what they're dealing with and what they can do about it. The LS engine family arrived in 1997 with the 5th-generation Corvette and represented something genuinely different in GM's engineering history. Where previous engine families had been evolutionary developments of mid-century architecture, the LS was a ground-up redesign that incorporated lessons learned from decades of small block development. It breathed better, it was lighter for its displacement, it had better oil control, and it demonstrated that GM's engineering talent, when properly directed and adequately resourced, could produce something legitimately world-class. The automotive press recognized it immediately. Enthusiasts embraced it with an enthusiasm that bordered on devotion, and the aftermarket community, the same network of independent mechanics and small performance shops that had spent decades cleaning up GM's compromises on previous engine families, looked at the LS architecture and saw something they hadn't seen before. They saw potential. But even here, in GM's most celebrated modern engine family, the familiar patterns were present if you knew where to look. The valve springs in the original LS1 were adequate for the engine's factory power output and factory RPM range, but they were marginal. Engineers who understood valve train dynamics could see that the springs were sized for minimum acceptable performance rather than optimum performance. Under sustained high RPM operation, valve float would occur at lower engine speeds than the architecture itself was capable of handling. The fix was straightforward: a set of upgraded valve springs that cost less than $200 and took an experienced mechanic an afternoon to install. The result was an engine that could safely rev to limits the factory calibration had been artificially constraining. The oil pump presented a similar story. Under hard cornering conditions, particularly the kind of lateral acceleration that the Corvette platform was theoretically designed to handle, the standard oil pump could experience cavitation, a momentary loss of oil pressure that left critical engine components briefly unprotected. The solution existed in GM's own parts catalog in the form of the higher capacity pump used in certain truck applications. It bolted directly into place. The cost difference was negligible. GM chose not to install it in the performance application where oil starvation under cornering loads was most likely to cause damage. Here's the thing about the LS engine family though. Something happened with it that hadn't happened with any previous GM engine platform. Something that changed the entire trajectory of the story. The aftermarket didn't just fix GM's compromises, they transcended them entirely. Companies like Texas Speed and Performance, Brian Tooley Racing, and Mast Motorsports took the fundamental LS architecture and demonstrated capabilities that GM's own engineers had never seriously pursued. 1,000-horsepower street engines became achievable with bolt-on components and careful tuning. The LS swap community emerged, dropping these engines into vehicles they were never designed for. From vintage muscle cars to Japanese sports cars to British roadsters, because the combination of performance potential, compact dimensions, and parts availability made it the obvious choice for anyone building a high-performance vehicle from scratch. The LS became, in the estimation of many serious automotive engineers, the small block Chevy of the new millennium. Not because of what GM built, but because of what the aftermarket transformed it into. And this raises an uncomfortable question that deserves to be asked directly. Did GM deliberately engineer the LS with room to grow, knowing that the aftermarket would develop that potential in ways that would generate ongoing enthusiasm and parts revenue without GM having to invest in the engineering themselves? It sounds like a conspiracy theory when you first hear it, but look at the evidence with clear eyes. The architecture was overbuilt in fundamental ways that suggested the engineers knew exactly what it was capable of. The factory calibration was conservative in ways that seemed designed to leave obvious performance on the table. And GM's performance parts division was positioned perfectly to capture revenue from enthusiasts who wanted more than the factory offered. Whether this was deliberate strategy or fortunate accident depends on how charitable you're feeling toward an organization whose internal documents we've already seen describe calculated approaches to managing failure rates for profit. What's beyond dispute is the outcome. The LS ecosystem became one of the most economically significant aftermarket communities in automotive history, generating billions of dollars in parts and service revenue, the overwhelming majority of which flowed not to GM, but to the independent shops, specialty manufacturers, and individual mechanics who had done the actual work of unlocking the platform's potential. Tom Milner had a shop in Nashville that specialized exclusively in LS builds by 2006. He had started as a general mechanic in 1994, working on whatever came through the door, accumulating the kind of broad diagnostic experience that makes a technician genuinely versatile. When the LS platform arrived, he recognized something in it that he hadn't seen in a production engine before. He recognized an architecture that rewarded understanding. Previous GM engines had been designed to a price point in ways that punished the people who worked on them. The LS felt different. It felt like something built by engineers who cared about what they were creating, even if corporate pressures had constrained the final execution in familiar ways. Tom's shop became a center of gravity for LS knowledge in the Mid-South. Mechanics would drive hours to talk through problems with him. He developed relationships with aftermarket manufacturers, feeding them field data about what was working and what needed improvement. He built a reputation that attracted customers from across the country who wanted LS-powered builds done by someone who understood the platform at a level that went beyond following instructions. By 2010, his waiting list was 14 months long. He had turned down partnership offers from 3 separate performance parts companies because he didn't want the business relationship to compromise the honesty of his technical feedback. What Tom represented and what the hundreds of mechanics like him across the country represented was a kind of parallel engineering institution that had emerged organically in response to GM's institutional failures. These weren't people who had set out to build an alternative to the factory. They were people who had simply refused to accept inadequate answers to questions that had better answers available. They had followed the evidence wherever it led, shared what they learned with anyone who needed it, and built reputations based entirely on the quality of their work and the accuracy of their knowledge. The C7 Corvette's LTT1 engine, introduced for the 2014 model year, brought genuine technological advancement. Direct injection, continuously variable valve timing, and an available dry sump oiling system for the Z06 variant represented a meaningful step forward in engine technology. The direct injection system in particular allowed for precise fuel metering that improved both performance and efficiency compared to previous port injection designs. It was legitimate progress. It also introduced a problem that anyone familiar with direct injection technology could have predicted, because it was a problem that had already been observed and documented on every other direct injection engine that had entered widespread production. Direct injection delivers fuel directly into the combustion chamber rather than into the intake port upstream of the intake valve. The practical consequence of this distinction is that the intake valves are never washed by fuel flow. In a port injection engine, fuel mist passes over the intake valve on every intake stroke, and this fuel flow carries away the carbon deposits that accumulate from oil vapor in the crankcase ventilation system. Remove the fuel wash, and the carbon builds up on the intake valve stems and the backs of the valve heads until it reaches a level that disrupts airflow, causes misfires, and requires physical cleaning to address. Toyota had dealt with this. Volkswagen had dealt with it. BMW had dealt with it. BMW had dealt with it. Every manufacturer who had deployed direct injection at scale had confronted this problem and developed approaches to managing it. GM's solution was to recommend intake valve cleaning as a maintenance procedure at 30,000-mile intervals. This was not an engineering solution. It was a maintenance burden transferred to the customer, a recurring cost that would extend across the entire ownership period of the vehicle for a problem that had engineering solutions available at the design stage. The most effective approach, used by several competing manufacturers, was to supplement the direct injection system with a secondary port injection circuit that restored fuel wash to the intake valves under specific operating conditions. The cost of adding this system at the design stage was a fraction of what customers would spend over a vehicle's lifetime on valve cleaning services. Mark Williams in Atlanta didn't wait for the failures to start accumulating before he developed his response. He studied the direct injection carbon problem on other platforms before the LT1 even reached dealership lots, and by the time the first C7 Corvettes were arriving in customer hands, he had already developed and tested a catch can system that intercepted the oil vapor from the crankcase ventilation system before it could reach the intake tract. $50 in components and 2 hours of installation time. The catch can collected the oil vapor that would otherwise coat the intake valves with carbon, eliminated it as a contamination source, and extended the interval between valve cleaning services dramatically. Customers who installed the system in the first months of ownership were still showing clean intake valves at 100,000 miles. GM's engineering response when they finally addressed the carbon accumulation problem in the LT2 engine that debuted with the C8 Corvette in 2020 was a supplemental port injection system, precisely the solution that competing manufacturers had implemented years earlier and that independent engineers had been recommending since the LTT1's introduction. The interval between the problem being identified and GM implementing the engineering solution was 6 years. The interval between a mechanic in Atlanta developing an effective workaround and GM implementing the factory solution was also approximately 6 years. These numbers are not coincidental. They suggest that GM's development timeline was influenced less by engineering necessity than by the accumulated pressure of marketplace feedback and competitive comparison. Here's what most people don't realize about the entire arc of this story. The mechanics who developed these solutions were not, in most cases, motivated by antagonism toward GM. Many of them were genuine enthusiasts who loved the vehicles they worked on, who saw potential in the platforms they specialized in, and who were frustrated precisely because they could see how good these vehicles could be if the engineering compromises had gone the other direction. Mike McViden in Cincinnati still drives a 1972 Chevelle with a built small block that incorporates every modification he's developed over 4 decades of working on these engines. He talks about that engine with the kind of affection that only comes from deep familiarity and hard-won understanding. He's not anti-GM, he's pro-quality, and he found that quality required supplementing what GM provided with what he knew needed to be done. The underground network these mechanics built, the forums and websites and personal relationships and shared knowledge bases represented something that had no real precedent in automotive history. Previous generations of mechanics had accumulated individual expertise that lived in their heads and their hands and was transmitted slowly through apprenticeship relationships. The internet allowed that knowledge to propagate at a completely different speed and scale. A solution developed in a Nashville shop on a Tuesday could be known to mechanics in 40 states by the following weekend. Failure patterns that would have taken years to accumulate enough cases for statistical significance could be identified in months when thousands of mechanics were contributing observations to a shared database. GM's legal department understood the threat this represented to their narrative about product quality, which is why Rick Santos received those cease and desist letters, but the knowledge couldn't be contained by legal pressure. It had already distributed itself too widely, embedded itself too deeply in too many independent repositories to be effectively suppressed. The mechanics had built something more durable than GM's press-fit galley plugs. They had built an institution. The story of how General Motors managed its relationship with quality across 4 decades cannot be fully understood without examining the cultural infrastructure that made these decisions possible. Engineering compromises don't happen in isolation. They don't emerge from the minds of individual bad actors making selfish choices in dark rooms. They emerge from organizational cultures that have developed systematic ways of normalizing decisions that would be obviously unacceptable if examined plainly and honestly. Understanding how GM built that culture, how it sustained itself across leadership changes and market cycles and near bankruptcy is essential to understanding why the backyard mechanics who opposed it were doing something more significant than fixing engines. They were opposing an entire institutional philosophy. The cultural foundation was laid in the post-war decades when GM was so dominant in the American market that competition functioned differently than it does today. In the 1950s and 1960s, GM controlled more than 50% of the American automobile market. When your market share is that large, the competitive pressure that normally drives quality improvement is substantially reduced. Customers who had a bad experience with a Chevrolet in 1962 didn't have many genuinely different options. Ford and Chrysler were operating with similar engineering philosophies and similar cost structures. Import alternatives were either unavailable or culturally marginal for most American buyers. The practical consequence of this competitive landscape was that GM could afford to optimize for cost reduction in ways that a company operating in a genuinely competitive market could not. The accounting frameworks that formalized this approach developed gradually through the 1960s and 1970s, reaching their most sophisticated expression in the decade following the 1973 oil crisis, when GM was simultaneously dealing with the need to develop more fuel-efficient vehicles and the pressure of significantly higher raw material costs. The response to these simultaneous pressures was a systematic effort to identify every component in every vehicle where the specification could be reduced without triggering immediate customer complaints or warranty claims. The galley plugs, the head bolt material, the transmission sungel. These were not random targets. They were the outputs of a systematic process that evaluated every component against a framework that balanced minimum acceptable performance against maximum cost reduction. Here's the thing about that framework that makes it particularly insidious. The people applying it were not, in most cases, cynical or malicious individuals. They were engineers and accountants doing their jobs within a system that rewarded certain outcomes and penalized others. An engineer who successfully reduced component costs by eliminating a specification that testing showed wasn't strictly necessary for minimum warranty performance received positive performance reviews and career advancement. An engineer who insisted on maintaining specifications beyond the minimum warranty threshold was spending money the system had identified as unnecessary, and that was a problem to be managed rather than a virtue to be rewarded. Frank Dettori spent 22 years as a powertrain engineer at GM's facility in Pontiac, Michigan, before retiring in 2007. He has spoken publicly about the internal culture he observed during his career, and his account is consistent with what the documentary evidence from bankruptcy proceedings revealed. He described a culture where the question was never what's the best way to build this component, but rather what's the minimum specification this component needs to meet to get through the warranty period without generating claims that will reflect badly on our department. The warranty period was the horizon. Everything beyond it was someone else's problem, specifically the customer's problem and the independent mechanic's problem. Frank describes attending engineering review meetings in the 1990s where field failure data from independent mechanics and customer complaints were systematically reframed as user error or improper maintenance rather than design inadequacy. The Dex-Cool sludge problem was consistently attributed to customers failing to maintain proper coolant levels or using incompatible aftermarket coolants rather than to the documented tendency of the coolant itself to become acidic in the presence of air. The Northstar head bolt failures were attributed to overheating events caused by customer neglect, rather than to the fundamental incompatibility between the thread engagement length and the material properties of the aluminum block under thermal cycling. This reframing served multiple purposes simultaneously. It protected GM from warranty liability by establishing a narrative that placed responsibility on the customer. It protected the engineering decisions that had produced the problems by ensuring that internal post-mortem analyses began from an assumption of user error rather than design failure. And it insulated the organizational culture from the feedback that would have been necessary to change it. Because if failures are always the customer's fault, there is never any reason to question whether the design that produced the failures should have been different. Now, you might be thinking that this kind of institutional self-deception has limits, that eventually the accumulated evidence of systematic failure would become impossible to deny even within an organization committed to denying it, and you would be right that the evidence eventually became undeniable. But the timeline over which that happened is instructive. The Dex-Cool class action settlement came in 2008, 13 years after the coolant was introduced with internal test data showing its problematic properties. The Northstar head bolt issue was never formally acknowledged by GM as a design defect during the engine's entire production run from 1993 to 2010. The 4L60E sunshell problem was quietly addressed in 2003 for commercial applications, while continuing in consumer applications, a partial acknowledgement that simultaneously confirmed the problem and demonstrated the ongoing commitment to managing it rather than solving it. The 2009 bankruptcy represents a genuine inflection point in this story, though not necessarily for the reasons that GM's subsequent public relations efforts suggested. The bankruptcy produced two things of lasting significance for understanding GM's quality culture. First, it forced the disclosure of internal documents that had previously been protected from discovery in individual warranty disputes, documents that provided the evidentiary foundation for understanding the systematic nature of the cost-benefit frameworks we've been discussing. Second, it created genuine existential pressure of a kind that competitive market forces alone had never produced, pressure that forced a reckoning with the question of whether the existing culture was compatible with the company's survival. Mary Brower's ascent to the CEO position in 2014 and her subsequent management of the ignition switch recall crisis demonstrated both the depth of the cultural problem and the genuine difficulty of changing it. The ignition switch issue, where a defective switch could cut engine power and disable airbags during a crash, had been known internally for over a decade before the recall. The internal investigation that Barra commissioned, led by attorney Anton Volukas, produced a report that used the phrase GM nod to describe a cultural phenomenon where engineers would acknowledge problems in meetings without any intention of taking action to address them. The nod conveyed the appearance of engagement while preserving the status quo. The Volukas report is worth reading in full for anyone who wants to understand how large organizations sustain cultures of deliberate inadequacy across decades and leadership transitions. It describes a system where information about problems flowed upward through the organization in forms specifically designed to minimize the apparent severity of those problems, where the language used in internal communications was carefully calibrated to avoid creating documentary evidence of knowledge that would establish liability, and where the professional incentives at every level of the organization reinforce the behavior of managing the appearance of quality rather than pursuing actual quality, rather than pursuing actual equality. Look, what the Volukas report described in the context of the ignition switch was not a new phenomenon specific to that component or that era. It was a mature, sophisticated institutional culture that had been developing for decades, expressing itself across every product line and every engineering discipline, producing exactly the patterns of failure and denial that mechanics like Mike McViden and Tom Caraway and Danny Rodriguez had been encountering in their shops since the 1980s. The ignition switch crisis was the moment when that culture became visible to the general public and to federal regulators. But the mechanics had been living with its consequences since before most of the journalists covering the story had started their careers. The aftermarket response to GM's quality culture created something that deserves recognition as a genuine social institution rather than simply a collection of commercial enterprises. Consider what actually emerged from the combination of consistent GM failures and independent mechanical ingenuity over 4 decades. A distributed knowledge base that documented failure modes with greater accuracy than GM's own internal quality systems. A parts supply chain that had developed upgraded alternatives to virtually every problematic GM component, manufactured to higher specifications than factory parts at competitive or lower prices. A network of skilled technicians whose expertise in specific GM platforms exceeded anything available through GM's own dealer network because they had accumulated knowledge through solving real problems rather than following repair procedures designed to minimize warranty exposure. This institution had no headquarters and no organizational chart. It had no official membership and collected no dues. It sustained itself entirely through the exchange of knowledge and the reputation effects that came from solving problems that the factory had created and refused to fix. Mechanics who contributed accurate information and effective solutions gained standing in the community. Those who overstated their knowledge or proposed solutions that didn't work lost it. It was a meritocracy of practical competence operating in parallel with and in direct competition to a corporate hierarchy that had organized itself around the management of appearances. The contrast between these two institutions illuminates something important about the relationship between genuine expertise and institutional authority. GM had the resources, the engineering talent, the testing facilities, and the production scale to solve every problem we've discussed in this video. The solutions were not beyond their capability. They were beyond their cultural willingness to implement because implementation would have required acknowledging that the problems existed, that the existing designs were inadequate, and that the customers who had experienced failures had been failed not by their own maintenance habits, but by deliberate engineering decisions made above their pay grade. The mechanics had none of GM's resources and all of their willingness. They acknowledged problems the moment they encountered them. They sought solutions without any institutional pressure to minimize or deny the severity of what they were dealing with. They shared what they learned without any concern for the liability implications of disclosure. And they built reputations, real reputations based on actual outcomes that proved more durable and more valuable than the brand equity GM was spending billions of dollars to maintain through advertising, while simultaneously undermining it through calculated engineering compromise. Steve Magnuson in Minneapolis put it in terms that have stayed with me since I first encountered them in a forum post from 2011. He wrote that the difference between a good mechanic and a bad one is the same as the difference between a good engineer and a bad one. The good one is more afraid of the problem than of the answer. GM had spent decades being more afraid of the answer than of the problem. The mechanics who fixed their mistakes had their priorities in the right order, and their engines showed it. The resolution of this story doesn't arrive in a single dramatic moment. There's no boardroom conversion, no engineering epiphany, no press conference where a GM executive stands before a crowd of mechanics and acknowledges 4 decades of calculated compromise. The resolution is quieter and more distributed than that, playing out simultaneously in thousands of garages and forums and small shops across the country, accumulating gradually into something that has genuinely changed the relationship between manufacturers and the people who buy and maintain their products. Here's what most people don't realize about where we are right now in this story. The underground network that emerged to fix GM's known problems didn't just solve those specific problems. It created a template for how enthusiast communities can function as a check on institutional failure at a scale that was impossible before the internet connected dispersed expertise into coherent collective knowledge. The mechanics who documented Vortec head failures and shared Sunshell upgrade procedures and distributed Northstar repair kits were doing something that extended well beyond keeping GM vehicles running. They were demonstrating that transparency and shared knowledge could accomplish what competitive market pressure and regulatory oversight had failed to achieve. The automotive landscape that exists today reflects this demonstration in concrete ways. Manufacturers now operate with the understanding that significant product failures will be documented publicly within weeks of their appearance in the field, shared across platforms that reach millions of people, and analyzed by independent experts whose credibility derives from demonstrated competence rather than institutional affiliation. The days when a manufacturer could manage a systematic quality problem through warranty policy adjustments and carefully worded technical service bulletins, keeping the full scope of the issue contained within channels they controlled, those days are functionally over. GM itself has changed, though the degree and durability of that change remains genuinely uncertain. The Zero Defects initiative that Mary Barra announced represented a real shift in stated organizational priorities, and there is evidence in the engineering of more recent GM products that some of the cultural patterns described in the Valugas report have been disrupted. The LT2 engine supplemental port injection system suggests that the direct injection carbon problem was addressed through engineering rather than maintenance burden transfer. The more robust lifter designs appearing in current generation engines suggest that the AFM failure pattern has been taken seriously at the design level rather than managed through parts revenue expectations. But here's the thing about organizational culture. It changes slowly and incompletely, and it tends to revert toward established patterns when the external pressures that drove the change begin to relax. The mechanics who have spent careers watching GM's institutional behavior are not uniformly convinced that the changes are deep enough or durable enough to represent a genuine transformation rather than a temporary adjustment to acute external pressure. Mike McVitin, still working at 73 years old, still modifying engines in that Cincinnati garage, puts it simply, he says he'll believe it when he sees 10-year-old vehicles coming in with their original components intact, and he's not holding his breath. The competitive environment that GM now operates in is genuinely different from the one that allowed the quality culture we've described to persist for so long. Toyota and Honda build trucks and SUVs that compete directly with GM's core product lines, and they compete on reliability in ways that are documented by independent organizations with enough data and credibility to influence purchasing decisions at scale. Hyundai and Kia have executed quality improvements over the past decade that have moved them from the bottom of reliability rankings to positions that directly challenge domestic manufacturers. Ford's Coyote V8 and EcoBoost engine families have demonstrated that American manufacturers can build engines that combine performance with durability in ways that don't require an aftermarket correction network to achieve acceptable longevity. This is where it gets really interesting because the competitive pressure that failed to correct GM's quality culture when it came from domestic rivals appears to be having more effects now that it comes from manufacturers whose entire market position in America was built on reliability reputation. When a customer choosing between a Silverado and a Tundra can access independent reliability data showing differential failure rates for specific components and can find forum discussions documenting those failures in granular detail with photographs and mileage records and repair cost documentation, the information asymmetry that allowed GM to manage quality problems through narrative control is simply gone. The backyard mechanics who built the knowledge infrastructure that eliminated that information asymmetry were not trying to change the automotive industry. They were trying to help the specific customers who came through their doors with specific problems that needed solving. But the cumulative effect of thousands of individuals making that choice to solve the problem honestly rather than accept the manufacturer's framing of it was to create something that functions as an industry-wide accountability mechanism. Every major manufacturer now operates in awareness of this mechanism, and the awareness shapes engineering decisions in ways that the previous generation of automotive executives never had to consider. Jake Morrison in Detroit still sells his Northstar repair kits. The demand has declined as the engine ages out of the active fleet, but it hasn't disappeared entirely because there's still Northstar-powered Cadillacs being maintained by owners who value them and want to keep them running correctly. Jake estimates he has now sold over 4,000 kits since he started offering them in 2005. 4,000 engines that got the repair they deserved instead of the replacement that would have failed identically. 4,000 customers who paid $1,500 instead of $8,000. The aggregate difference in what those customers spent versus what GM's recommended solution would have cost them exceeds $4 million. One mechanic with a drilling jig he designed himself redirected $4 million from GM's parts revenue to customers' pockets, simply by solving a problem that GM had decided was more profitable to leave unsolved. That number, multiplied across every upgraded sunshell and threaded galley plug and catch, can installation and Dex-Cool flush that the network has collectively performed over 4 decades represent something genuinely staggering. The mechanics didn't just fix engines. They transferred wealth from a corporation that had calculated it could extract that wealth through planned inadequacy back to the customers that corporation had decided to exploit. They did it with drill presses and thread taps and 15-cent brass plugs and the stubborn conviction that problems have solutions and solutions deserve to be shared. What's the worst GM engineering decision you've personally encountered? And did you find the fix before the dealer got involved? Drop your story in the comments below, because the knowledge that lives in this community is exactly the kind that keeps these vehicles on the road and keeps the people who maintain them honest. And if you want to keep going deeper into the engineering decisions, the corporate calculations, and the garage discoveries that have shaped the vehicles we drive, subscribe to Legacy Motoring, because we are nowhere close to done pulling back the curtain on what Detroit built, what it knew, and what it chose not to tell you.